Okay, here we are on the fourth module. And in this module, we simulate what the response would be on the detector. And this is in a scan direct absorption technique where we scan over a small wavelength range, wave number range, across the features that we're targeting. And for every period, we have an upscan, downscan, and so we were able to trace out the absorbance for a very tiny, one wave or one nanometer approximately in wavelength space. So here we have module 4. We've already ran module A1, which is the local setup. Module 3 walks you through the simulation of absorbance using HITRAN. So here we build on that and then simulate what the response would be on the detector, the actual data we collect. So here we do some setup. We use the same, here's the generate absorbance spectrum function from the module 3. So here's kind of there's the simulation of the drive signal, which is, essentially the injection current to the laser. So that part's not too complicated. We're just choosing a sinusoidal function. I talk a little bit about it here. There are, in practice, you can use a triangular or sawtooth waveform for this kind of sensor. That can be simulated too. I just kind of went with a sinusoid just because the math is simpler, and then in terms of how we estimate the output wavelength of the laser, it's a lot simpler, but it's something that could definitely be done if it's sawtooth, for example. And in this case, so here's the modeling of the drive signal, the injection current. And so just simple sinusoid, down scan, up scan, and I'm just assuming here 2 volts max on the detector. Or actually it kind of speaks to a little bit of the specifics on how these lasers are driven. There's typically a transfer function that, it's depending on how much voltage you apply to the laser driver is going to correspond to milliamps. So voltage to milliamps transfer function, and that tells you how much the laser will actually span in terms of wavelength range. So those are some more hands-on specifics. Here we're just going to talk about what the driver signal would look like in terms of voltage. Okay, so the other pretty key part of this modeling of the detector is, okay, so as we have this sweep in voltage, that's going to correspond to a certain sweep in wavelength or wave number, frequency. And so the major assumption that we've made here is that it's pretty much proportional to the intensity of the drive signal. So this is kind of the major assumption here. And for the frequency of these simulations, this is sub-second scans, for example. If you're thinking about an application like atmospheric methane sensing, then that's probably okay. Depending on the application, this may be too slow or too fast, but if we just assume 10 hertz as your scan frequency, then there's assumption that the output wavelength is changing correspondingly with the amplitude of the drive current or drive voltage is probably pretty accurate. If you start moving into the kilohertz, tens of kilohertz range, then the thing to do would be to just actually measure that response instead of trying to guess at how the output wavelength changes with your drive current. Then you can just measure it using an etalon, and you would actually have you wouldn't have to make any assumptions. You'd have a direct measure of how the output wavelength changes with time. This is kind of just a general way of doing this since we're simulating it. Okay, so around that, this is just the part that maps the two, is wavelength to time. So then we can go ahead and just plot the output. Depending on the drive voltage, you're going to see a similar change in wavelength, in wave number. So then, now that we have a mapping from wave number to time, we can, for certain conditions, we can go ahead and plot what that looks like for transmitted intensity. So here's what the incident intensity would look like. Here's how wave number is changing over time. The absorbance versus time. So we're scanning across, then coming back. So upscan, downscan, however you want to look at it, downscan, upscan. And so then the transmitted intensity, this is what it would actually look like on the detector. And so just kind of a note here that we're going through and essentially passing over the same wave number region twice. So if you were to overlap what the absorbance looks like versus wave number, you just have an exact overlap. In practice, when you are using a laser like this, there's it's never perfect, but for the most part, you're capturing the same features on the upscan as the downscan. Sometimes there's a small shift depending on how the laser reacts to your input. But for the simulation, we're not accounting for any of those slight nuances. So initially, when I started doing this, I was just doing like a very quick matching of nearest neighbor on the wave number array. But then, the whole goal is to get to 1 million scans for your data set. So you want to try and optimize some of the code wherever you can. And so we've vectorized this. Essentially, just you make the wave number vector array consistent. And so then it just allows you to be able to march through there a lot faster. And so it kind of just compares here. In order to run the simulation for the old quick method, it's about 0.228 seconds. With this vectorized form, it's 2.5 times faster, with zero difference in terms of what the outcome is. So, and that kind of just if we did 1 million scans. With the loop version, it would take 63 hours. With the vectorized version, 24 hours. So you save time where you can. And so then here is a demo just to kind of showcase what this looks like for a couple different cases. Here's standard conditions, and it just kind of illustrates what the baseline versus transmitted intensity looks like. This error here has to do with once you get down close to zero here, you have some NANs, and so it doesn't like it when you divide by that. And then another one here is just tiny dip when your mole fraction is real small. tiny dip in the transmitted intensity. And yeah, and so then what you can do is similar to module 3, you save this as a CSV file with our format here that contains the temperature, pressure, mole fraction. And so this is really going to be the foundation of this data set generation. It's going to be essentially vectors of this transmitted intensity versus time. And we'll start stacking those up to a million to kind of, use as a training set for the model. That's it. I hope you find this helpful.